Yeah.
Oh, that's cool.
Oh yeah.
So, class, so let's go ahead and start. I'm trying to get this up. I want to make a video of today's class because some of the stuff is covered in the book, but not very much in depth. So I wanted to do a video. If you think you can get this, I had it a second ago. I'm not sure what's going on. I need this HDMI to hook up. If you want to.
I think that's it right there.
No, it's not, because it should be coming from here. That's the problem.
Okay.
And I had it working a second ago. Let's see.
Do you want it to come from your laptop?
Yep.
Okay.
I've done this a couple of times. Okay.
Let's go ahead and
And I thought it might have been because the connection wasn't.
Wait a minute. That's your problem right here. Okay, so do you have a mouse? Drag that over. Okay, wait. Go to the easier way to do it. You probably want to go this.
Yeah.
And you want
You're right. It is something like that.
okay, so it is your. This is your computer screen.
Yeah, but it just did it a second ago. That's the weird thing. That's why I don't
Go ahead
understand.
and display settings. And then we're going to go to this thing. Let's say this is duplicate.
Thank you, sir.
All right.
Okay, so let's get started. Okay, a couple announcements. Okay, a couple announcements. The exam I'll probably post. I'm going to look at the survey results today. So if you haven't put in the time that you want for exam 2, let me know. The choices are November 6th, November 8th, which is a Monday and Wednesday. Okay, so I'm going to go ahead and look at those today. And based on what I see, I'll make a decision. So if you have one date that's a lot better than the other, just let me know, okay? It's one of those days. I got scalded by coffee, and
Oh, that's the worst.
it's tough coming back after vacation. Okay, so any questions before we get started on anything? The homework's due this Friday. Everyone knows that? Everyone's good on that. Okay. Okay, so what I want to do is I want to pick up on exponential decay. And like I said, some of the stuff I'm going to talk about is not in the text or not covered quite as well. So I'm going to go through that. First thing I want to review is what we talked about last time. The important part for you as budding engineers is that you understand a couple of facts. You understand that this is the basic differential equation for exponential growth or decay. And what we showed last time was we showed that to be a solution of this equation means that you have a function, not a number, a function that you put in and satisfies this. And last time we showed that this function was a solution, and then we claimed that it's the only solution. And there was a proof in the book, okay? The reason why we want to know that this is the only solution, so this is the unique solution, is the fact that when we see this, we automatically want to be able to write this. So you give me this differential equation, ask me what the solution is. I don't have to worry about there being 2 or 3. I know that there's just one and exactly one. Okay? And then we talked about the fact that K tells us what that equation is doing, if it's decaying or growing. And so I want to get to where we left off last time, okay? So we started talking about how exponentials are used in financial growth. We kind of stopped here last time. I want to show you a few examples. This is stuff that isn't in the book, but I think it's kind of good to know. So the first is dealing with compound interest. And the idea is that if you put $100 in the bank and you have an annual interest rate of 6%, that's compounded yearly. What that means is after every year, you get 6% of whatever you put in at the beginning of that year, right? So after 1 year, you have your $100 plus the interest, right? So 6% of 100 is just going to give us $6. Now, it's very rare that you see something compounded annually, okay? So if you look at, for example, $100 and you have an annual interest rate of 6% that's compounded monthly, what you do is you're going to divide the annual interest rate by 12. That's going to be your monthly interest rate. And so you can see that money multiplies the same way that bacteria does. It doesn't double every month, but it is multiplied by 1.005 every month. Okay. So again, a population is a very, very general concept. It doesn't have to be bacteria. It can be a population of money in a bank. And so you can kind of follow this argument, and you see that every month, all you're doing is you're multiplying by this factor. Whatever you had the month before, you multiply by 1.005, and that gives you the amount of money next month. And so you can kind of see that there's this pattern. It's the same as bacteria. After the first month, you multiply the 100 by this factor. After the second month, you multiply this factor times what you had at the end of the first month, which is this, and you end up getting that factor squared. It's exactly like the bacteria growth rate problem. And after 12 months, that's going to tell you how much money you're going to have in the bank after 1 year. Okay? So any questions about compound interest? Yeah?
The only thing, what does K represent in the equation for the Y0 K?
We're going to get to that. So this is a good question. Now we know what the general equation is. We're going to see if there's actually an exponential equation that ends up going with that. But we're going to have to do a little bit of work to get there. Okay, so here's going to be one way of looking at a formula. And this is a good thing to think about. So to kind of go to Tobias's question, it turns out that every exponential rate problem has both a form as a general exponential function and the exponential function. Usually, when you're dealing with things like bacteria and interest, the general exponential function is the easiest, okay? So this is exactly what we did. And now we just kind of mathematized it, right? We're going to write this in symbols. We're going to say that the amount we have after m compounding periods is just equal to this factor. This is the yearly interest rate, R, divided by the number of compounding periods in 1 year. If you think about what we just did a second ago, in our last example, right? Our R was 0.06. This was the yearly interest rate. Our N was 12. This was the number of compounding periods per year. And our M was the number of months. So we happen to have 12 months. This was the number of months. So this is the amount of time in months, okay? So this is the time. So this is the number, we'll say the number of compounding, total number of compounding periods. Okay? And of course, our a sub 0, the thing that's always multiplying that general exponential function is going to be the amount we started off with, okay? So our a naught in that problem is 100. And if you look at this, you'll realize that this is actually a general exponential function, okay? If I want to, I can write this function like this. I could write it as a of t is equal to 1 plus r over n. And now I'm just going to write m as t, the total time divided by the number of compounding periods, okay? So t might be in years, and I'm going to divide that by n times a sub 1. And this, it turns out, is actually useful for a couple of reasons. So I'm going to do a little more mathematical stuff here. And now I have a general exponential formula. Okay, this is going to be the general exponential formula. And there's a really super cool fact that we're going to see in a little while. We're going to see that we can turn this into the exponential function also. But the point is that I can always write this as a general exponential function. Okay? All right. Any questions about that part? So what we'll end up seeing when we're actually talking about the exponential function, what we're doing is we're letting the compound period go to 0. And that's what you hear as when people talk about continuously compounded interest, that's what they're talking about. And we're going to see there's a really cool theorem that links this formula to the exponential function. It's kind of hard to prove. I think they give a proof in the book. I think I give one in the back, but it's kind of hard to prove actually. Okay. And again, this is online and I have a video made of this. So if you don't get it all done, that's okay. Okay, so we can just do a really quick example. This is stuff that's kind of useful to think about when you're doing financial planning and stuff like that, which you want to do as soon as you graduate. Okay, so on your 25th birthday, okay, you have a rich uncle, it's nice, gives you $10,000, right? And you put that money in a bank account, it pays an annual interest rate of 2%, it's compounded monthly. And so you want to know, if I just let that money sit, I don't touch that, okay? Wait till retirement, how much am I going to have at age 65, all right? Now, in real life, annual interest rates are pretty low, so it's like below 1%, but you know, since it's your birthday, we'll let you dream. Okay, so let's go ahead and work this problem out. So if I think about this, A naught's my initial amount. I know that's 10,000. I know that my annual interest rate is 2%. I always write that as a decimal. You don't write that as a percentage. And I'm told that it's compounded monthly. And the way I translate that is I'm going to have n compounding periods. Okay. So this is the number of compounding periods in 1 year. This is what monthly means, right? And now all I have to do, I have everything in the formula, I need to figure out m. Well, m is just the number of times that money had to multiply, okay? So if I think about what m is going to be just equal to the number of months in, and I'm letting it be invested for 40 years, right? This is the number of compounding periods, the number of periods like the bacteria gets to duplicate, right? And I can do that. That's just 480, right? 12 times 40. Now just plug it in our formula. And so when you do this calculation, you end up finding that after 480 months, you have 10,000. 1 plus 0.12, 480. This comes to about 22,000 when you just put this in and do the calculations. About 22,240 number of dollars. So it's about a doubling period. So if you invest something at 2% interest, after about 40 years roughly, it's going to double. That's a long time. Okay. So the formula is pretty easy to use. Now, here's a kind of fun example. And before I do that, I just want to I want to show you something kind of interesting, which is that as the compounding period gets smaller and smaller, the amount of money that you make gets bigger and bigger. Okay? So if you have money that has an annual interest rate of 6%, you invest it for 3 years, and the compounding period is 1 year, that's less than if the compounding period was monthly, and it's less than if the compounding period was continuous. And I haven't convinced you that this is the formula for continuous, but I will in a little bit, okay? And that's why all banks tend to use continuous or compounded interest. You tend to use more discrete, like when you're lending money to like one of your relatives or something, like then you compounded yield or something like that. But banks use continuous or compounded interest. Okay, and we're going to get to the exponential part in a minute. We'll show how that comes about. Now here's a kind of cool thing, and if you guys want to, you can do this for extra credit. I'll give this as an extra credit cost for class. So what happens when you're in college? Well, I know what happened when I was in college. No one had credit cards, and all of a sudden everyone had them. And people were spending like crazy, right? Buying pizzas on credit cards and whatnot. So let's just take an example where you buy an iPhone for, I don't know, just make up some amount, $750, okay? And the credit card companies are really nice. They only ask you to pay the minimum. Only pay $15 a month, right? Sounds like a great deal. And you decide to do that, okay? So you only pay that minimum balance, okay? And the thing you have to remember, the way they make their money is, while you're waiting to pay it off, what's happening to your balance? You're charging interest on it, right? So it's growing, okay? So if you look at most student credit cards, the interest rate's pretty high, okay? It's usually a little higher than 1.4%. So the question is, how long does it take you to pay off a phone if they're charging you 1.4% interest and you only pay a minimum of $15 a month? So it's kind of an interesting problem, right? You're taking money out each month and they're increasing the balance, all right? And if you go through this, if anyone wants to, you want to write a program or whatever, you're free to do it. So I'll give you extra credit if you can duplicate this plot. And this plot is basically looking at the amount that you spend on the phone. So the amount that you spend on the phone goes up linearly, right? Every month you're paying $15, okay? So this is a linear function. And if you look at your balance, it goes like this, okay? So you're decreasing it because you're paying on the phone, but it's not going down at a linear rate because there's interest being charged. And it turns out that in the end, you end up paying like 7 years for the phone, which all phones are obsolete after a couple of years, right? And you end up paying roughly about $1,300 for a $750 phone. So you basically spend about twice as much as the phone's worth. So the moral of the story is don't make the minimum payment, okay? But I'll leave that as extra credit. If you can duplicate, if you can show me the code and duplicate that picture, I'll give you extra credit. Okay. Right. Questions on that? Yeah, twice.
Can I go with B and C?
You can do it however you want. C, MATLAB, Excel, they all work. Pick your poison. Okay. So the last thing I want to look at is radioactive decay. So there are a lot of problems in the book on radioactive decay and temperature decay. So again, we start off with the same sort of formula. So it turns out just the laws of physics, laws of quantum mechanics, that radioactive material decays according to this law. The first thing you should realize is the sign of K is negative because we're decaying, right? So we know here that K is going to be negative. But one thing I can automatically do, because I proved uniqueness, I didn't prove uniqueness, I claimed uniqueness, right? I claimed uniqueness, and we did show that this was the initial amount. I can write down the general formula. And this is important, because M naught's the initial amount. And usually I'm given that in a problem, okay? The problem usually reduces down to finding K. So here's what I know. Let me write this out really explicitly. So when we're dealing with the radioactive decay problem, it's going to have this form. I know that K is less than 0. I know two things. I know K is less than 0, and I know the solution has this form. And this is the initial amount that I start off with. Now, it doesn't have to be at time equal to 0. I'm thinking of time starting somewhere, okay? Maybe I happen to come in right now and measure the amount. That's my M0, okay? It's the amount at some specified time, and then I'm watching it decay. Now, we did this before when we knew the half-life, okay? But we may not know the half-life. So last time when we worked this problem, we actually talked about this in the context of bacteria, right? We said that if we know the half-life, and I'm just going to call this tau. People call this tau 1/2. Okay. I know the amount at any time t. It's this. I can actually write out the formula. Here, there's nothing to figure out. If I know the half-life, I can get that formula. Because what is t over tau 1/2? It's the number of halving periods. Okay? Just like we had a doubling period for bacteria, after every half-life, what that means is you have half of what you had before that period elapsed, right? So I can write something like this. So this is, you could think of t over tau 1/2 as the number of, and for lack of a better word, we'll say halving periods. So you start off with some initial amount, you wait tau 1/2, you have half of that, you wait another period, and you have half of that. And as Heather Locklear says, and so on and so on, so on.
What did you say after initial?
Initial amount. That's what we start off with. So usually it's m of 0. It's the amount you have at time 0. If you're in physics, sometimes people write this like this. They just write it as m sub 0. Okay, it's the same thing. So we know how to do this when we're given the half-life. When you're given the half-life, you can automatically write that formula. When you're not given the half-life, then it's going to be more work. So we're going to see how to do that. Okay. Oops. So one of the things we're going to want to do is sometimes we want to write it as a general exponential. Sometimes we want to write it as an exponential. Okay. So we can actually determine k from the half-life. So let me go through this formula. If you're given k, I'm sorry, if you're given the half-life. So suppose we're given the half-life, but we want to write the solution as an exponential function. And I'm going to put the exponential function. How do we do that? And this problem is an important problem to focus on, because we're going to use a little trick that may not be totally obvious. So let's start with what we know. We know that after one half-life, we're going to have I'm going to write this as m tau to the half is equal to 1/2 whatever I started off with. So what I'm thinking here is I'm thinking that I started off at some time 0 when I started to first watch it. I had m sub 0. I waited one half-life, and the amount I had now was m sub 0. Okay. But I also know what the formula is. I also know that it's this. I'm sorry. Yeah, let me write this way. And I just happen to put t is equal to tau of 1/2. I know that. And I'm going to set these two things equal. Okay. So actually, I want m of t as this. Sorry. So this is at any general time. This is at 1/2 life. Okay. So I know this is my general formula. And I know everything in here. I know the amount that I started off with, and I know the half-life. So I have to know a few things. What I want is I want to be able to write this like this. This is what I want. I want to be able to write this as the amount at some time is equal to the initial amount times e to the kt. So I want to write this as the exponential function. The question is, how do I do that? Well, I'm just going to set these two things equal and solve for k. So I'm going to set these two expressions equal and solve for k. So I know that m of 0 is 1/2 t divided by the half-life. And this is equal to m naught e to the kt. Okay? So now I'm just going to solve for k. And when you do this, it's not hard. You take the natural log of both sides. And now you use some properties of natural logs. Okay. I can use the fact that I can always bring the exponent out. And the natural log of an exponential ends up canceling out. Okay. And if you want to, you can use one little trick that we didn't talk about, but it actually follows from the division trick. You can use the fact that the natural log of 1 over any number, call it x, is equal to natural log of x. And this actually follows from our rules about natural logs of quotients, right? This is a natural log of 1 minus a natural log of x. The natural log of 1 is 0. So I can go ahead, I can cancel my t's, and I end up getting that k is equal to minus log 2 divided by the half-life. So that's a handy little formula. If I'm given a half-life, I can go ahead and get k. And I usually know what the initial amount is. Okay? You can see that k is negative. That's the reason why I rewrote the log of 1/2 as minus the log of 2. Okay, because I really want to emphasize that here, this is positive, and that's negative. Okay. Any questions on that? Those manipulations? Okay. So let's just do a quick problem. Suppose you're told that the radioactive material fermium has a half-life of 3 days. You put 10 grams of fermium in a test tube. You come back 2 weeks later, how much is left, okay? Now, in this sort of problem, I'm free to do this however I want. I didn't say use the general exponential function. And I notice a couple of things that are important, okay? I notice that I'm given the half-life. So this automatically tells me what formula to use. I'm going to use the halving formula, okay? This automatically tells me I'm going to use this formula right here. I'm going to take whatever the time is and divide it by the half-life. Something to be really careful about is that, you know, I'm going to have to convert whatever time I have to the unit the half-life's measured in, okay? So what do I know? I know the initial amount's 10 grams. So here's the picture that we're thinking about, right? We start to look at it at some time, This is our M0, that's 10 grams. And then I wait, a certain period elapses, right? 2 weeks. And I want to know what is the mass here. And I'm going to express the mass in days, right? So an important thing to realize is that whenever you take an exponential function, it has to be unitless. So the units have to cancel. So the units here are days for the half-life. So I'm going to have to convert t to days. But that's easy. 2 weeks, right? So this is 14 days. And now we just go ahead and put this all in and just do the calculation. 10 times 1/2 to the 14th. And you go ahead and compute that out. And you get, we're gonna expect this to be a pretty small number, right? Because you're having it 14 times, so that's gonna be pretty small. And you end up getting roughly 61 grams.
Shouldn't it be 14 divided by 3?
Oops, my bad. Thanks. Yeah, thanks. I was thinking it was 1 day. Thanks. Let's see, what did I do? Yeah, I forgot to redo that. Okay, so I'm going to have 4 2/3. Well, I will just compute that out, right? 14 to 3. Let's go ahead and do that real quick and see what it is. We'll just do it in Excel really quick. One thing you have to be careful when you do these calculations, and the book doesn't talk about this, is that you never want to round things off, okay? Because these things, they get big and fast really easily. So 10 times 0.5 raised to the 14 divided by 3. Thanks, Glenn. Okay. Yeah, so now it's not. So now you only had 14, you only had roughly like 4 halving periods. So you can kind of do that in your head, right? You started off with 10, after 1 halving period 5, after another it's going to be 2.5. Okay. Okay, thanks. So it's about 0.3 now, roughly. So you have to put the right halving period in. Okay. So this part's not too bad. Okay, it's just like the bacteria problem, really.
What would the units be?
Right, the units here are going to be the units of the mass, whatever it's in. So here, if we started in grams, it's going to be grams, right? And if it got really small, you might want to do milligrams, micrograms, whatever, right? Okay. And we just went through this formula, okay, of how to get this. I want to show you this though, because this is a problem that requires you understand something that may or may not be so obvious. So this is a problem, and this is how they actually do radioactive dating. Okay, notice that when the dinosaurs died, okay, depending on what you think, when the dinosaurs died, there was no one there to observe how much was in them. Okay, but here's how the scientists do it. This is really cool. They can go back in their records, and they can estimate the amount of radioactive carbon that was in the atmosphere. They claim they have ways to do that, all right? So they can estimate how much radioactive carbon was in the air. And it turns out that you're in equilibrium with your surroundings. So if there's whatever percent of radioactive carbon in the air, it's going to be in your body. So they know how much the dinosaurs had at a certain time. They don't know when that was, okay? And then time elapses. And they can now figure out today how much is in their system, how much is in that fossil, right? And so then they can figure out the percentage, and they can actually estimate the half-life. So let's see how they actually do this. So here's kind of the picture. And so this is called, you know, carbon 14 dating or radioactive dating if you use something other than carbon. So here's kind of the picture here, right? So here's some dinosaur, right? And it's chomping on something, right? And they actually know how much C14 was in his system, but we don't know the time. And then it dies, gets fossilized, whatever, and then they can measure the amount. So this is today. They can measure the amount of radioactive carbon, and they know what percentage is left. Okay, they know how much should have been here. They know how much is here. They just don't know how much time elapsed. And so you can figure out how long that fossil's been dead, and you can kind of estimate how long ago those animals lived. So let's go ahead and try this. So here's what we know. We know that the half-life is this many years, and we know the percentage of the initial amount, okay? So I'm going to write this like this. We know that there's 35% of the initial amount. So T is the time today. And I want to know what is T. That's the problem. It turns out it's not that hard. Because I also know something else too, right? I know this is equal to and I can set those two things equal. Okay. So notice I have two things I can use now. I know that the amount today is this amount, but I also know from the laws of radioactive decay that it has to also be equal to this. And now I can just work the problem out and figure out T. Okay? And so if you do that, you can see something really cool, which is the initial amounts cancel out. So I'm left with 0.35 is equal to 1/2 T over the half-life. And I know what the half-life is. We'll just go ahead and write it in. And I can go ahead and solve for T now. How am I going to get T? What do I have to do? Whenever I have a variable I want to solve for in the exponential, right, I'm going to have to take the natural log. So I just take the natural log of both sides. And so I'm going to get T divided by this times the natural log of 1/2. And if you work this out now, I'm going to multiply by 5730 and divide by natural log of 1/2. You're going to find out that T is equal to times natural log of 1/2. And when all the mathematical smoke clears and you put that in, you find out that ends up being roughly about 8,678 years. Which of course is probably way too young for that. Okay. That's how radioactive dating works. Okay. It's kind of cool. Any questions about that? Yeah, Charles.
Do you know how much carbon-14 was originally in the dinosaur?
Yeah, I don't know how scientists know that. So they claim they have somebody that's that. But how, I don't know. That's a good question.
What is the 5,700?
Okay, so this we do know. So this is the half-life of carbon-14. Yeah, and that's just from physics, okay? We can determine that from physics. All right. So last we come to a really interesting problem. I was thinking of this today when I got scalded with water for my coffee. Here's my problem. Help me out with this. I was running late, of course, because everything's going wrong today, right? I made my coffee. It was too hot to drink. And here's the thing: I got to do two things in the morning. I got to shower, and I got to shave, and I got to drink my coffee. I need to have coffee. 3 things. I have to get dressed too. All right. Here's the problem. My coffee's too hot to drink, and I gotta go shower. What should I do? Should I let my coffee cool down while I shower and then put the cream in? Or should I put the cream in first and then shower and let the coffee cool down?
I'd shower first.
Shower with the coffee. I speak from experience.
Which is going to cause it to cool down.
Shower, so we got nothing better to do. Well, what if you're taking really long?
So it actually depends. The answer is it depends. Suppose I don't put a lot of cream in, and it's the temperature of the refrigerator. It's actually a hard question to answer, but there's kind of a principle. What determines whether I let it sit or I put the cream in first?
How long the shower is.
Okay, that matters. Okay, but it turns out, well, okay. Well,
it's the difference between the like the room and the temperature of the coffee.
Right. So Newton, one of the other things he discovered was that the rate at which the temperature decays is dependent on the difference. So the way we say this in physics is that the rate depends on the gradient. That's the physics way of saying it. In other words, the difference between the coffee temperature and the room temperature is what dictates the rate. The greater the gradient, the greater the temperature difference, the faster it decays. So I should have, and I did, though it's hard to shower without coffee, I did shower first and then I put the cream in second. Because the temperature difference is greatest before I put the cream in. Although the details of that can kind of depend upon, like you say, how much cream or whatever. Okay, so that's the idea behind Newton's law of cooling. So this is a genius of Newton, or one of the other cool things he did, was he figured out that the rate at which you decay, so this is the temperature of the body, and this is the surroundings, okay? The rate of decay depends on the temperature difference. The greater the temperature difference, the greater the rate of decay. By the way, it also works for heating too. It works the other way around. If you have an ice cube sitting out, the same sort of law applies, okay? So it's both cooling and heating. He was a cooling and heating guy. He did both. All right, here's a really cool problem I want to show you before we end, okay? And it turns out, and this is what you're going to need for the homework. If I can get it on the screen. Okay. It turns out that this is the formula. Okay. It turns out that this is the formula. This tells you at any time t what the temperature is. So again, just like the radioactive dating, right? I observe the temperature at some time. That's t equal to 0. Okay, so that's the time when I know the temperature, and I want to know what it is at some other time. And this is the surroundings. And of course, k is negative. I'm doing a decay, right? And so you notice something really interesting. The whole problem boils down to finding what? K. That's all I have to figure out. Okay. I'm generally given the amount at some time. I obviously know my surrounding temperature. I have to find K. Now, and again, I put this up here, and this is on a video, but I want to show you a really cool thing before we end. This is how people determine time of death. So this is an example. This could be a real life example. Okay. So the cops come and they discover a corpse. Okay, a mysterious corpse, of course. It's a road solver, right? Very dramatic. At midnight, no less. And what they do is, if you watch a coroner takes the body temperature. So the cops come in, coroner comes in, whatever, medical investigators. He measures the temperature. It's 80 degrees Fahrenheit. And then the cops go out and do their quote-unquote investigation. They get done, that's right. Come back. And this is what they do in real life. They wait a little bit and they take the temperature again at some specified time. And from that, they can determine when the corpse died. So I think this has extra credit for you guys. Here's the basic problem. Let me sketch this out, okay? So here's what's going on. And this is why I say it works for both heating and cooling. So this is midnight. This is our time t equal to 0. And they find out the temperature here, we said, was 80 degrees Fahrenheit. And then they wait a little bit longer. They come back 2 hours later, and they find it's 75. So this is equal to T of 2. And they know that the surrounding temperature is 60 degrees. Yeah.
And so we also know that the human body is a temperature of 98 degrees.
Right, we got to know one more thing. That's right. So we know two more pieces of information. We know that the surrounding temperature is 60 degrees Fahrenheit. And what we knew is when the person died, way back here, they should have been around 98.6.
It's something like that. But because of the way physics of the fighters, it takes a very long time for that to cool down.
Yeah, it's exponential decay, right? So the trick is to figure out whatever that question mark is. When did they die? So it's going to be a negative time, right? Because 0 is at midnight. It's going to be a negative time. And if you turn that into, I'll give you guys extra credit. So you got 2 extra credit problems to work on. Because homework's not due till Friday, right? So I wanted you guys to have something to do. You know, I didn't want to deprive you. All right, that's it for exponential. We're going to pick up with 3.9 on Tuesday. All right, thanks. And by the way, I'll post the video too if you guys want to.